Hello, MATSE 112. How you doing? So I'm in the Washington, D.C. airport getting ready to board my flight to Europe and then on to Saudi Arabia, and I don't have lots of time, so this is going to be quick and we'll see how it turns out. So as proof, this is a British Airways 747 right there. That one's going to Heathrow. I'll be on a different plane headed to Frankfurt, but you can hear the announcements and other interesting things going on here in the International Terminal in Dulles. So we have a couple more electrochemical things to wrap up, and today you're going to have a video from me, and then Chris is going to give you a quiz, and this is a real quiz. It'll help you practice some of the things that I expect you're going to be able to do on the third exam. So I will continue to help you through the exam. Of course, the homeworks are great practice for exam number 3, but please treat this quiz as a real exam situation, and we'll see how far you can go. I will look at them myself because Chris is going to scan them and email them to me, and then we'll keep going on like this, and I have a good plan for the week. So anyway, I want to emphasize this slide right here, and that shows the oxidation of a metal. So you can see metal M goes to metal 2+, and so you see here's the metal right here, and it's going to metal 2+ ions in solution, and then this metal is in contact with HCl, or hydrochloric acid. And so what's being oxidized normally is the metal, and you see that reaction, and then protons in this case are being reduced. So you know that protons really like to be reduced, and when protons are reduced they generally go to hydrogen. So what's important in this slide is that now you can see the interfacial reaction. So all electrochemical reactions have to happen at an interface, because you need electron transfer from the metal to whatever's being reduced. And so that's highlighted right here. So this is a solid metal or an electrode, and you notice we have electrons moving through the metal from the oxidation reaction to the reduction reaction. And those electrons are the electrons involved in the half reactions. And so you know that in oxidation reactions, electrons are products, and those products from oxidation reactions are used in reduction reactions, where electrons are a reactant in reduction. And so please make sure you understand this, and you also understand that you have a solid metal or a solid electrode in contact with a liquid electrolyte, or again, electrochemical reactions are generally interfacial reactions. There has to be an interface in order to get these reactions to occur. So study this, think about it, and also you can relate this now to oxidation of metals, or rusting, or corrosion, and all the things we saw previously for oxidation of a metal by various pathways. So please take a look at this and remember this. Also, because we're dealing with chemical reactions, you know that we can calculate the thermodynamics of these electrochemical reactions. And so thermodynamic affinity is something that we can talk about in terms of the driving force of the delta G. So you know that delta G doesn't give you any kinetic information. Remember, potential in delta G is a thermodynamic quantity, and current is the kinetic quantity. And so remember that thermodynamics provides no kinetic information. We're going to talk about current a little bit more, either when I continue this lecture when I'm in Germany, or we're going to talk about kinetics on Wednesday for sure, and talk about specifically what's important about current and how we use current with Faraday's law to compute how many moles of something has been reacted. So anyway, the thermodynamic affinity is just the delta G of these electrochemical reactions. But that's interesting to think about, because we have this table right here, and you see the oxidation reactions of all these various metals, whether it's iron, chromium, nickel, copper, etc. These are some of the corrosion reactions that are important that we care about for various metals of interest. And you can see in this table that some of the delta G's are really negative, right? Negative 1,000 kilojoules per mole, negative 200 kilojoules per mole, negative 800 kilojoules per mole. So these reactions are all thermodynamically favorable. And because the delta G is so negative, you know that the equilibrium constant is very, very large. So in a lot of ways, just like combustion reactions, these electrochemical reactions have a high driving force to the products. And so we know that iron rusts, we know that other metals corrode, but in certain situations it doesn't happen very quickly. So you take a metal and dip it in acid and bubbles are coming off. That's pretty fast electrochemical reaction. But iron oxidation or rusting is really slow. So you can't see rust form in real time. So you can't look at the bottom of a car and watch the rust form. But it's got a really large negative delta G. So the driving force for rust to form is large. But the kinetics are very slow. Think about that in relation to something like hydrogen combustion. So hydrogen plus oxygen is water. You know that that also has a negative delta G. It's about negative 280 or 250 kilojoules per mole, something like that. However, if you put hydrogen and oxygen together and you give it a spark, boom, you get a very fast kinetic explosion. And so that's kinetics. The driving force is there. The delta G is negative for both iron oxidation and hydrogen combustion. But the kinetics of iron oxidation are very, very slow, whereas the kinetics of hydrogen combustion or hydrogen oxidation are very, very fast. And so think about that as you try and separate in your minds thermodynamic driving force described by potential or delta G, and the kinetics or how quickly something will happen. So this just gives you a little bit of an idea of physical situations, how we compute the thermodynamic variables that we know a lot about, and then in real life, what happens? What happens to an oxidation reaction? How fast is it? What happens physically during a combustion reaction? Why are the kinetics fast? Why is it useful? So I'm going to check in again, but I have to go catch my plane right now. So I'll be back with a little bit more explanation of kinetics in a couple minutes.